There are over a dozen ways humans have learned to turn fuel, steam, or electricity into motion. Some power your car, some launch rockets into orbit, and a few you've probably never heard of. In the next 11 minutes, we'll break down every major type of engine ever built, how each one actually works, and why it exists. Let's start at the very beginning. At its core, an engine is just an energy converter. It takes stored energy, usually chemical energy in fuel, and turns it into mechanical work, something that spins, pushes, or thrusts. Every engine on this list does that one job. What makes them different is how they release that energy and what they do with it. Engineers split them into two big families: external combustion and internal combustion. We'll start with the older one. First up, the steam engine, the machine that powered the Industrial Revolution. The idea is beautifully simple. You burn coal or wood outside the engine to boil water. The steam expands with enormous pressure, pushes a piston inside a cylinder, and that piston drives a wheel. Because the fuel burns outside the cylinder, this is called external combustion. Steam engines are heavy and slow to start, but they're incredibly reliable, which is why they ran trains and factories for over a century. The steam engine's modern descendant is the steam turbine. Instead of pushing a piston, high-pressure steam blasts through rows of curved blades, spinning them like a windmill at thousands of RPM. It's far smoother and more efficient. Here's the part most people don't realize. Most of the world's electricity, from coal, gas, and even nuclear plants, is still made by spinning a steam turbine. The fuel just changes, the turbine stays the same. Now the second family, internal combustion, where the fuel burns inside the engine itself. This is the technology in almost every car, truck, and motorcycle of the last 100 years. The breakthrough was moving the explosion right next to the piston, making engines smaller, lighter, and far more powerful. The most famous version runs on a 4-step cycle. Meet the 4-stroke gasoline engine. Its cycle has 4 steps, and engineers remember them as suck, squeeze, bang, blow. Step 1. Intake. The piston moves down and pulls in a mix of air and fuel. Step 2. Compression. The piston rises and squeezes that mixture into a tiny space. Step 3. Power. A spark plug ignites it. The explosion forces the piston down. This is the stroke that actually makes power. Step 4. Exhaust. The piston pushes the burnt gases out. Repeat this thousands of times per minute across multiple cylinders, and you get a smooth, powerful engine. The diesel engine looks similar but pulls off a clever trick. It has no spark plug at all. Instead, it compresses air so hard that the air itself becomes hot enough to ignite the fuel the instant it's injected. This higher compression makes diesels more efficient and gives them huge low-end torque, which is exactly why trucks, ships, trains, and heavy machinery run on diesel. The trade-off is they're heavier and run rougher than gasoline engines. Then there's the 2-stroke engine, the loud, smoky little powerhouse in chainsaws, dirt bikes, and jet skis. It does the whole cycle in just 2 strokes instead of 4, firing twice as often. That makes it lightweight and powerful for its size. The downside? It burns oil mixed with the fuel, so it's dirty and inefficient, which is why it's been banned from most modern cars but still rules small, simple machines. Here's the weird one, the Wankel Rotary engine. It has no pistons going up and down at all. Instead, a triangular rotor spins inside an oval chamber, and as it turns, it creates the same 4 stages: intake, compression, power, exhaust, in different corners at once. The result is an engine that's tiny, smooth, and revs incredibly high. Mazda famously used it in the RX-7 and RX-8. But it guzzles fuel and wears out its seals quickly. So it stayed a rare cult favorite. Now we leave pistons behind entirely and enter the world of jet propulsion. Engines that don't push, they breathe. The principle behind all of them is Newton's third law. Throw mass backward fast and it shoves you forward. Let's see how a jet engine turns burning fuel into raw thrust. The original is the turbojet. Air rushes in the front and gets squeezed by a series of spinning compressor blades. Fuel is sprayed into this compressed air and ignited, creating a continuous, controlled fire. The hot gas explodes out the back through a turbine, which spins the compressor up front, keeping the whole cycle going. What shoots out the nozzle is a screaming jet of exhaust. Simple, brutal, and fast, turbojets powered the first supersonic fighters. But turbojets are loud and thirsty, so engineers added a giant fan to the front and created the turbofan, the engine on virtually every airliner you've ever flown on. Most of the air the fan moves bypasses the core entirely, going around it. That bypass air provides most of the thrust, much more quietly and efficiently. That huge spinning disc you see when you board a plane, that's the fan of a turbofan, gently pushing tons of air backward every second. Two close cousins use the same hot core differently. The turboprop sends almost all its power to spin a propeller, perfect for smaller, slower regional planes that need efficiency over speed. The turboshaft instead routes that power to a shaft that spins a helicopter's rotor. Same beating heart, three different jobs: a fan, a propeller, or a rotor. Every engine so far has one thing in common: they all need air to burn fuel. But there's no air in space, so how do rockets work? A rocket engine carries its own oxygen, called an oxidizer, on board. It mixes fuel and oxidizer in a combustion chamber, ignites them, and channels the violent expansion through a bell-shaped nozzle that accelerates the exhaust to incredible speeds. That's why a rocket works in the vacuum of space where a jet engine would simply die. It's not pushing against the ground or the air, it's pushing against the mass of its own exhaust. This is the only engine on this list that can take you to the moon. Now for the engine quietly taking over the world, the electric motor. Technically, it's a motor, not an engine. But it does the same job with almost no moving parts. It uses electromagnetism. Send electricity through coils of wire and you create a magnetic field. Arrange those fields cleverly around a rotor and the constant push and pull of magnets makes it spin. No fuel, no explosions, no exhaust, just instant torque and near-silent operation. It's far simpler and more efficient than anything that burns fuel, which is exactly why electric cars accelerate so hard and need so little maintenance. Of course, you don't always have to choose. A hybrid combines a small combustion engine with an electric motor, letting each do what it does best. The motor for quiet city driving, the engine for long highway range, and on the horizon are engines burning hydrogen, which emits only water and even ion thrusters. Engines so gentle they'd struggle to lift a sheet of paper, yet they push spacecraft across the solar system for years on a tiny puff of charged gas. The future of engines isn't one winner. It's the right engine for the right job. So let's bring it all together. External combustion gave us steam engines and the turbines that still light our cities. Internal combustion gave us gasoline, diesel, two-stroke, and the strange spinning Wankel. Jet propulsion gave us turbojets, turbofans, turboprops, and turboshafts. Rockets broke free of the atmosphere entirely, and the electric motor is rewriting the rules with no combustion at all. Every one of them solves the same problem, turning energy into motion in its own brilliant way. From a boiling kettle that moved a nation to an ion engine drifting between planets, engines are how humanity decided to move. If you learned something new, there's a whole series of these breakdowns waiting for you. Subscribe, and we'll see you in the next one.